Welcome to today's lecture. Today we are going to continue from where we had left in the previous lecture. In this lecture, we will study the process involved in design of machine foundations. Machine foundation design is essentially a multidisciplinary activity. Basically, three different engineers and the associated engineering domains are involved in this process. The first is mechanical engineer, who is from the manufacturing domain. Then the geotechnical engineer is involved. Both the mechanical engineering and geotechnical engineering inputs, they are transferred to the structural engineer, who is finally involved in the design of the machine foundation. Now let's see what inputs are provided by the mechanical engineer and the geotechnical engineer. The mechanical engineer must provide the magnitude, location and direction of the forces generated by the machine at the points of anchorage on the foundation, because these are then made use of by the structural engineer for the design. At the same time, it is also expected from the mechanical engineer, who is basically involved with the design of the machine, to make sure that minimal forces are generated by the machine while operating, and wherever possible counterbalancing is there. We'll understand in detail what and how counterbalancing can be applied. And finally, the mechanical engineer also specifies the limits on the displacement amplitude which can be withstood by the machine, because all machines, they are sensitive to vibrations, and it's the mechanical engineer who specifies the limits on the displacements. If no limits are specified as such, then the structural engineer, he will just make use of the code of practice. The geotechnical engineer, he carries out the geotechnical investigations of the soil on which the foundation is to be constructed. So essentially, the geotechnical engineer provides the location and depth criteria, and the engineer also specifies what type of foundations are suitable for the particular soil. Then if shallow foundations are applicable, then the geotechnical investigation report provides the allowable net bearing pressure, and in case of pile foundations, the pile capacities, compression, tension and horizontal are provided along with their dimensions. Finally, the stiffness parameters of the soil, they are also provided by the geotechnical engineer. So here both static as well as dynamic parameters are required. Now in this course we will also study how especially the dynamic parameters of soil can be determined experimentally. In case the soil investigation report only provides the static parameters, then the structure engineer can also determine the dynamic parameters. Now it is the onus on the structural engineer to analyze the soil foundation system suitably, model it and find out the stresses generated. So the stresses generated in the soil must be lower than the allowable net bearing pressure at any cost, and in case of pile foundations, then the forces actually generated in the piles must be within the limit specified by the geotechnical engineer. Then the structure engineer must make sure that the vibrations are under limit. Under limit means that they should be less than those specified by the mechanical engineer, that is the manufacturer, and they should be within the limits to ensure safety of the structure as well as comfort of the user. The structural engineer must make adequate arrangements in the concrete of the foundation so that the machine can be adequately anchored. So after the foundation is constructed and the machine is installed over it, then it's also the responsibility of the structure engineer to check for vibrations while the machine is under operation, and for this purpose necessary measurements are to be made, and it is to be ensured that the vibrations in the surroundings of the foundation as well as on the foundation are within the limits. Now let us study the general design guidelines. Now here there is a major difference between the building foundations and machine foundations. Building foundations are predominantly subjected to static loads. They are of course subjected to dynamic loads such as earthquake and winds, but for relatively smaller durations only, and that also not very often. Machine foundations on the other hand are subjected to very small static loads, and they are subjected to very high dynamic forces in contrast to the dynamic forces on building foundations which act only occasionally. The dynamic forces are continuously acting while the machine is under operation in the case of machine foundations. Let us list the important considerations which are necessary in the case of machine foundations. The first most important consideration is that the foundation should be able to carry static as well as dynamic forces with adequate factor of safety against shear failure. That is, the stress should be within the safe net bearing capacity, which is decided based on the shear strength of the underlying soil. So this must be satisfied under both static and dynamic conditions. The next important consideration is that the settlement under the foundation for both static and dynamic loads together must be within safe limits. So the pressure corresponding to the settlement criteria is called as the safe bearing pressure. So essentially the allowable net bearing pressure is supposed to be the lower of the safe net bearing capacity and the safe bearing pressure. So these pressures are to be specified in the geotechnical investigation report. The geotechnical engineer does the investigations and the calculations as per IS 1904. The next important requirement for the foundation is that structural engineer must ensure stability of the foundation. In general, the machine is anchored on the top of the foundation. Foundation itself consists of block resting on a wider base. The machine, the block and the base, they have individual centers of gravity. It should be ensured that all the three center of gravities, they lie on a single vertical line to ensure overall stability of the system. If these CGs, they are lying on the same vertical line is not possible, a maximum of 5% of eccentricity could be allowed. The next most important design consideration is the avoidance of resonance. Because the machine is continuously operating, it's very important that its operating frequency should be away from the natural frequency of the system comprising of the machine, foundation and soil. For this purpose, we compute frequency ratio R, which is the relative frequency of the machine with respect to the natural frequency of the machine, foundation, soil system. So we use the symbol F subscript M to denote the operating frequency of the machine and F subscript capital N to denote the natural frequency of the system. You must have been aware of the amplification factor in the case of single degree of freedom system under external force. This concept you must have studied in your structural dynamics course. So if we draw a plot of the amplification factor A as a function of the frequency ratio R, then we get a plot something like this. So here the value of R equal to 1 signifies the resonance condition and value of R equal to 0 signifies static condition. So from the static condition to the resonance frequency there is a peak, and the value of the amplification factor increases from 1 onwards. Then after achieving the peak at frequency ratio R equal to 1, it goes down. As far as the machine foundations, especially the block foundations, are concerned, then there is a zone with the values of R from 0.4 to 1.5, that is a prohibited zone. Hence, the structural engineer must ensure that either the frequency ratio lies less than or equal to 4, or it is greater than or equal to 1.5, and values in between the two, 0.4 and 1.5, should be avoided. So this is in accordance with IS 2974 part 1, which is specially for block type foundations. Machine foundation design is an iterative procedure. We may assume certain dimensions, and after the calculations we may find that we are lying in the prohibited zone. If, for example, the value of the frequency ratio is greater than 1 but less than 1.5, that means if we reduce the stiffness of the system, then Fn will go down, and that will increase the ratio and take the point to the right side of the prohibited zone. Similarly, in case the frequency ratio is lying in between 0.4 and 1, then it's advisable that we increase the stiffness of the system so that the natural frequency Fn increases, and that brings down the frequency ratio to less than 0.4. In this course, we'll study various technical ways of achieving these. The next important consideration for the structural engineer is to limit the amplitude of vibrations. Because the machine is continuously vibrating, it induces vibrations in the surrounding floor and also the various components of the building structure. There is a limit on the maximum amplitude of the displacement, and this must be satisfied. Here again there are two considerations. The manufacturer of the machine may specify a limit on the vibration displacement amplitude which is safe for the operation of the machine itself. For example, certain machines, they specify a limit such as 50 microns for the longevity of the machine and its safe operation. Other consideration for limiting the vibration amplitude is from the user point of view. Here again, the limits could be with regard to the safety of the supporting structure, because vibrations are continuously transmitted by the machine to the structural system, so that must be under control. And the other consideration is the comfort level of the user. This figure, which is taken from IS 2974 part 1, shows the various limits enforced on the displacement vibration amplitude. Here the limits are varying depending on the type, whether it's to avoid damage to the structure or to avoid serious discomfort to persons or to ensure reasonable comfort to persons. Accordingly, different curves are there. For example, the line ADD dash, this specifies the limits with the consideration that if we are within these limits, then safety of the structure is ensured. Then the stricter limit comes if we choose the next limit, that is to avoid serious discomfort to persons, and this is defined by the curve ACC dash. Finally, if we adopt the next strict criteria, then that is defined by the curve AB dash, ABB dash, which specifies the limit ensuring reasonable comfort to persons. So these three variations are there as per IS 2974. Under all circumstances, the maximum upper limit imposed on the displacement amplitude resulting from machine vibrations is 200 microns. This must not be exceeded in any circumstance. So these different curves, they can be adopted depending on the situation. In any case, there should not be any compromise with the safety of the structure. The limits for ensuring reasonable comfort to the persons are also equally important, because continuous exposure to vibrations may affect the health of the person, and the person may be prone to diseases such as heart trouble. Now a judicious choice is to be made, that is limit to avoid serious discomfort to persons and the limit to allow reasonable comfort to persons depending on the situation. Plants which are very less frequently visited by persons, then we may choose a higher level of disturbing amplitude of vibrations. The next important design consideration is to control the forces generated by the machine itself. The onus for this lies with the manufacturer, especially the mechanical engineer who is involved with the design of the machine. So the manufacturer must ensure that minimum possible unbalanced forces they are generated when the machine operates. Now this can be achieved by suitably and intelligently configuring the vibrating and the rotating masses. And here the concept of counterbalancing comes into picture. So the manufacturer may adopt the principle of counterbalancing wherever possible. Now how this principle works is explained here, that let's say there is a rotating type machine and it has an eccentric mass undergoing rotations. Now as the mass undergoes rotation, this process will generate forces which have both horizontal and vertical components, because the mass is rotating, so the inclination of the resulting centrifugal force is continuously changing with time. However, instead of one big rotor, the manufacturer might adopt two small rotors which are synchronized and they are undergoing rotations in the opposite directions, such that the resulting centrifugal forces from the two rotating masses, they act in such a manner that at least the horizontal component is cancelled out. Now this gives a big relief to the supporting foundation, because now the overall force acting on the foundation is only vertical force, and it imparts a very high degree of stability to the machine. Imagine a horizontal force acting at a certain lever arm, so that imparts not only just the horizontal force but also the moment on the foundation on which the machine is supported. So in this way, the designer of the machine must explore the possibilities of warding off at least the horizontal component of the forces. Now number 7 is very important, that any foundation design must keep in mind the possibility of any possible future expansion in the plant. The onus for this lies jointly on the client and the manufacturer of the machine. They must communicate to the structural engineer, so that at the time of the design of the foundation, all these considerations are kept in mind, say for any future piping or any future anchorage points, they can be incorporated at the time of the construction of the base foundation itself. So thank you very much. If you have any questions, you can discuss them during our interaction in the MST.